ever. Yeah. Intense. It's the same thing we did yesterday, but I did did the harder ones.
You should have brought in
Yeah. We'll do that later this year. How about? All right. So this guy, I don't think the first three terms are the issue for these. I wanted to get practice with the general term. So, for this type of problem, if you had to write a power series. Oh, there was guys, there was a question yesterday about like, how do you know whether you're doing like the derivatives with the factorials, you know, like the Taylor polynomial. Like in the problem, it'll ask you to create a Taylor polynomial or a Maclaurin. Like they'll say it in the directions. If they're saying like this kind of thing where it says a power series, like if they use that terminology, you should be using like your like background, like your go-tos, OG Maclaurins to come up with them. So like cosine, you know the power series for, so like cosine x is how you start it. So you would do, what is that, 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And then how many I need? 3 terms. So, well, maybe I'll do an extra one just to be safe in case one goes away. And then dot, dot, dot. And then we have alternating, even with the factorial. So you start with your cosine, and then they want k of x, they want cosine x squared. So we've done one like this before, but we didn't really do it with the general term, so I just want to make sure we know how to do that. So basically you just plug in x squared in wherever there's an x. So what I've seen people do in the past is they put, like, 1 doesn't have an x, so don't put anything there. You just leave it, like 1 stays. You're just plugging in x squared wherever there's an x. So that's happened on tests before. And I plug in x squared, x squared, x squared. And then as far as the general term, all the n junk, you just leave it. Like everything's messed up with the x. So like the -1 and the 2n thing, that's not changing at all. It's only the x that changes. So it's the same idea where you're just going to throw in, you know, x squared, just like all the other ones in there. Right. So, I'm going to run out of room. So the next thing you're going to do, because they want the power series for x, k to the x. So this one, the difference is now you're going to be plugging in or multiplying everything by x. So now this guy is going to turn into an x because you're multiplying everything by it. The numerator on the one before is x to the 4th because you multiply the powers. And then you multiply by another x. So that's going to be x to the 5th over 2 factorial. I guess I don't need the 6th one, so I'm going to skip it. And then the 4 one, it's x squared to the 4th, so that's x to the 8th. And then another x would be x to the 9th. And then we'll work with this general. Again, I'm skipping the 6th one because they only want 3. I just did the 6th one to be safe, you know, in case like one got rid of it or whatever as I'm doing stuff. So again, everything's happening with the x. So like all this n junk, you just leave it because nothing's going to happen there. So you got this, you got the 2n factorial, all that stuff didn't change. All the x stuff changes. So what happened is we multiplied these powers, right? Because you did like 2 times 4 is 8, right? So that'd be 4n, right? You multiply it. But then when you multiply everything by x, you add to the power. So this was 4 before, now it's 5. This was 8 before, now it's 9. This would be 12, the add 1 would be 13, so it's 4n plus 1. And that'd be the answer. So, okay. So, I don't know, that might be kind of weird with exponent rules, but you never know. Okay, so these next ones are like these, number 7. Remember when everyone started crying? This one. So when you're given, like, you have to do, like, natural log stuff, or look at that one. Ew. Okay. What you're going to have to do is, like, think about derivatives and antiderivatives of your OGs, of your Maclaurens. So, like, this one, what you can just, like, pull out of your brain, you know, is if you were to do this guy, right, this would be, oops, 1 plus x, right, like plus c, right? So if you were to integrate the 1 over 1 plus x, now I made you guys memorize them because then you have kind of like extra padding on the AP test, in case if you forget how to do stuff, you have them in your brain. But the way you can figure this out is using that geometric one we did the other day. This guy, this 1 minus x. Because you can always make the 1 over 1 plus x into the minus x. Yeah?
Can you explain, like, why does 1 over 1 plus or, like, minus x just equal, like, x plus x squared plus x cubed?
Oh, that's going back to, like, you could do, like, the Taylor polynomial where you take the derivatives all the time, centered at 0. So, like, if you plug 0 in, you get 1. And then if you take the derivative of that,
it works.
and then you plug 0 in, you get 1. And then you get 2. And then over 2 factorial. So, like, it ends up working with the Taylor. But then another way to think about it is it's in the same form as geometric, where because this one is like that's your R.
Okay.
I don't know if that helps. Like, this is like in the form. So there's like a couple ways to think about it. I don't know which one sticks, but
Okay, yeah.
that's where it comes from. Otherwise, like, back to this one, again, like, you can kind of, if you know how, like, here, maybe I'll do it over here. I'll put it in a different color. Like, the sum for stuff, it would be like 1 over a over 1 minus r, right? What you can kind of do is mess around with that 1 over 1 plus x and write it as 1 over 1 minus negative x, right? Like, then it looks more like my geometric series. So then what I can do is, like, if you think about how that's set up in your series, like the definition of a geometric, it would be, not x yet. This is like the formula for geometric, like that's what the form of it is, and it would just have you be plugging in a negative x there. So long story short, the 1 minus x is all this addition, right? The reason the 1 plus x is alternating, it's basically the same thing, but it changes sign, is because you're plugging in a quote-unquote negative r. Do you know what I'm saying? Like, when you rewrite it like this. So you're plugging in like a negative x in here, so that's why it has that alternating piece to it. So again, you have this one theoretically memorized, like 1 over 1 plus x is 1 minus x plus x squared minus x cubed plus blah, blah, blah. But really, it's just taking the negative r part of it out. That's because your r is negative. So the 1 minus x is all positive because your r is positive x. Whereas like the 1 plus r or 1 plus x is alternating. They just took the negative piece out of the r. So then now, as far as like, if you had to integrate this, so if I need to find natural log, because again, that's what I need to find, is I'm going to integrate this 1 over 1 plus x dx, and you're just doing, again, an antiderivative of all of it. So it'd be x minus 1/2 x squared plus 1/3 x cubed. Look at me knowing how to do exponents today. Yesterday, that was a struggle. Oh, I only need 3 terms. I guess I'm just going to stop there. And then plus dot, dot, dot. And then same idea, like this keeps like alternating signs. So like this -1 stuff's not going to be messed up. It's only the x that we're doing integration and derivatives of stuff. So if you think about how do you do an antiderivative, it would be x to the n plus 1 all over n plus 1, because you add to the power, divide by the new one. So that would equal, this is the same thing as natural log 1 plus x, like what I need to find, because it's the antiderivative of 1 over 1 plus x. So it's like you're using your OG Maclaurens and messing with them. So if you know their derivatives, antiderivatives, you should be fine with how you find them. Okay. All right, this one is a little juicier. Because look at this thing. Isn't that disgusting? Okay. So, yeah.
On the AP test, since you made us memorize like the actual like Maclaurens for ln1 plus x, do we have to do all that extra work, or could we just go straight to the first 3 terms?
I'm not positive. I'm not positive. I would have to get back to you, because I think it's only a 1 point or 2 points maybe. So if you know them, I think you should be fine. But yeah, but this is where they come from at least. They usually, this one, I think that one's too easy, believe it or not. They would usually do like this one, you know. So this is the strategy for natural log ones. Okay, because your natural log is this. And what you want to do is do your rules. Do you remember all these? Yay! Minus, and then, yeah, let's do pink. Right? And what you want to notice is we already did this one. Oops. Okay. Notice how we already did it. So, to get the beast done, we're going to have to take the one I found. So this is from the other problem. I'm just rewriting the stuff we wrote down. And then we're going to have to subtract that guy, which I don't know what that is yet. But it looks like something. Do you know what I mean? Like if you did, I mean, you know the 1 over 1 minus x, that's like one of the OGs, you know? So like the way I kind of reason through this one is like, okay, if I were to integrate 1 over 1 minus x, I know I'm going to get a natural log thing that looks like that, right? Well, kind of chain, right? If I integrate that, it'd be natural log of like 1 minus x and then like plus c, but I'm not kind of rewriting that right now. But because I have to do chain on it, so it's negative. right? Because of the negative x in here. The 1 plus x, it didn't matter because it was just positive 1. But like this one, I've got the chain on it. So I have to think here because it has to be negative natural log. So, okay, if it's minus, this now is going to change to a plus, right? Because if I integrate it the way I'm going to attack this thing, and what I'm going to do is I'm going to integrate the 1 over 1 minus x series. So the 1 over 1 minus x is the 1 plus x squared plus x cubed equal whatever. Oh, I only need, well, let's do an extra. Right? Because the antiderivative of this is negative, that's why I made it positive. So then I took care of the negative already with everything. So then, oh, look at this thing. We'll be fine. Okay, I guess I have to rewrite this because I got to do the antiderivative.
You need to put like the formula, the plus, da plus that.
Yeah. Yeah. Because we have to deal with the general term, which will be interesting. We'll see what happens, right? We're just kind of rolling. All right, so what is this thing? If I do antiderivative, I get x plus 1/2 x squared plus 1/3 x cubed. Okay, I'm going to stop because I only need 3 terms. You know what I mean? So I'm not going to go with that. And then what would this one be? The x to the n. So that would be x, add 1, divide by the new one, right? Okay, now I got to add that together. So, okay, what is happening? Okay, they're repeating. Wait a sec. Stuff goes away, right? Okay, wait. But the odd ones go together, right? Because they're both positive. Okay, so here we go. Evens cancel, right? Like these guys, those would cancel. If I kept going, there'd be more of them. But the odds, there's 2 of them, right? So that's another way to think about it is doubling. Is that fair? Because like 1/3 plus 1/3 is 2/3. So that'd be like the same thing as 2 times 1/3. So they'd all double. So, okay, now the general term we're just not going to look at right now. So we'll figure that out later. So we need, okay, we're going to have to double the odd ones. So I'm going to put a 2. And the odd ones are x, the 1/3. Oh, shoot, now I need another one, right? I only have the 2, so I need a third one. So the next one would be the 1/5, right? So it would be 1/5 x to the 5th. Is everyone okay with that? Okay. And then, okay, now I'm having to come full circle here. So so what do all these have in common? I mean, right now, I'm not really looking at the general terms themselves. I'm looking at the pattern of these numbers. Right? So we talked about the odds, right? So all the x's with odd powers, and remember the form, like the little expression for odd, was 2n plus 1. That means odd. So this means odd, okay, all over, and then all the denominators were odd. And it would be the same, like it's the same odd number as the exponent. Do you know what I mean? Like the 5 and the 1/5 and the 3 and the 1/3. No, plus, because you want odd numbers.
Oh,
Because if you plug 0 in, because we're doing, Maclaurin's, so you're going to start 0, and then you want the first power for x. That's a good question, though.
Because the natural log form starts on this one.
Yes, but the series starts at 0. Because you're plugging 0 in for n, you can't plug 1 in for x. Well, you can, okay. Your n and x are different. So like the n's are always 0, 1, 2, 3, 4. The x's are like whatever value you want to find on the graph.
Yeah, from absolute value.
Yep. So then grand finale is distributing. And don't do anything dumb like divide out the 2's. You guys wouldn't do that, right? Never. That would be a little cool comment.
That'd be really
Or death. It would be nice. It would feel satisfying. But oh, I got this from all these. And then like technically this one is a 1. Do you know what I mean? Yeah. So you like match it with the power. Do you know what I'm saying? Does that make sense?
Yeah.
Okay. Good. Anything else? Because this was kind of beefy. Okay. It's fun stuff. This is a nice one. It's like cute. Like if you have to do the derivative of that, you just take the derivative of it. But only pay attention, like don't be weird with the ends. When you take derivatives with respect to x, you're only dealing with your x junk. Do you know what I'm saying? Because everything else is constants and numbers and stuff. So what you're going to do, if you took a derivative, you would bring down the power and subtract 1, right? And there you go. There, that's it. Isn't that pretty? See, that one's cute. Yeah, it does look scarier. So, and they didn't ask me for like terms and stuff, so I'm like, meh, being done. Okay, this guy. This is what made me question the other problem. Okay, so p of x is this goofball thing. Okay, write a 4th degree Taylor polynomial for the integral about x equals 4. Okay, so, oh geez. All right, so I need a 4th degree Taylor polynomial. What? We're back here again? Okay, so maybe I'll do a different color so we're happy about it. So remember the notation for that. Sometimes they use p for polynomial. Sometimes they use T for Taylor. You just roll with it. And I put a little 4 because they want 4th degree. Okay? So if I need g of x, right, obviously it's integrating that function. So what I'm going to do is I'm going to integrate from 4 to x. And if you think about it, if you need a 4th degree, I'm going to use the polynomial that goes up to 3. Does that make sense? I'm only going up to the 3 one because if you integrate it, it's going to go to a 4, right? Like the cubing one is going to go to a 4 when you integrate it. So this is just like notational stuff to hopefully like get you solid here. And then what I'm going to do is I'm just going to throw in the crazy, the 7. That's what I was saying. So like if you're doing a cubic, if you integrate it, it's going to go to 4. So I'm just like, because honestly, half the battle with some of this stuff is getting the notation and figuring out what they even want you to do. So I'm not gonna do the last one is what I'm telling them. Oops. Oh, why did I change it to X? I'm sorry. I gotta have my variables be different. Okay.
Did you leave out the 6? Oh, it's 3 terms?
Yeah. So I didn't want to bother with the second one or the last one because I'd only need
Okay.
4. Up to 4. Okay, now this is the part which made me question everything. When you take an antiderivative, so maybe I'll just focus on this guy. So like if I were to focus on just this first part, like we're going 4 to x and then it's 7 dt, right? So I'm just kind of putting this off to the side so you can see why I'm going to say what I say, okay? Is this turns into 7t, right? From 4 to x, right? And then you get 7x minus 7 times 4, right? Is everyone alive? Right? Like normal antiderivative. And now to make it look cute, you can write it like factoring out the 7s. Do you see what I'm saying? So this first term in the series is going to be 7 times x minus 4. Okay. And then this one, it's just like normal antiderivative. So 3/2 x minus 4 squared plus 5/3 x minus 4 cubed minus 1/2 x minus 4 to the 4th. And then this would be the answer. We're done. That was the last one.